So let's imagine that we've estimated the propensity scores. So we now have this new column in our data set. And now we want to think about how to use those propensity scores to what I'll call equate the groups, to make them similar to one another. There are three broad classes of methods, at least as I think about them. There are matching approaches, weighting approaches, and subclassification approaches. In this short lecture, we're not going to get into those details. We're going to talk through an example of matching, so you'll see what that looks like in practice. Weighting, just briefly, essentially uses a function of the propensity score as a weight to weight the treatment and comparison groups to look similar to one another. And subclassification at a very high level basically forms lots of small groups of people with similar propensity scores and compares outcomes within those sort of small groups. One nice thing about propensity score methods is that you can try multiple approaches and pick the one that works best in terms of creating covariate balance in the data set. So you don't have to commit to one, you can try a few. So let me tell you what we did in this suicide example. In this example, we did what's called 3-to-1 propensity score matching. So what this means is that for each treated individual, each of those about 6,000 people, we found the 3 individuals with the most similar propensity scores who also were what's called an exact match, i.e. had the same values for 2 variables in particular, whether the individual had any psychiatric disorder and then whether they had a previous deliberate self-harm attempt. So in this sense, we're basically trying to find people, comparison individuals, who look exactly like the treatment individuals on these 2 variables, and then who look similar on the other variables that were used to construct the propensity scores. In this example, the 3-to-1 propensity score matching made sense in part because we had such a large pool of comparison subjects. We had about a 10-to-1 ratio, so we had 10 potential comparisons for each treated subject, and so it was in some sense easy to find 3 people who looked like each of them. Another nice thing about matching is that it's fairly easy to explain. It's sort of pretty straightforward to say we have these 6,000 people and then we found 18,000 people who look like them on these covariates. You don't have to explain weighting or subclassification. It's pretty straightforward. And another benefit is that the outcome analysis is then quite straightforward in that you basically take the treatment group and their matches and compare outcomes across those. And we'll see an example of that as we move along. So one thing that's helpful to do just to get a sense for the propensity score distribution and what methods might make sense is to look at what's called the overlap between treatment and control groups on the propensity score. What this is going to show, as I'll show in the next slide, is basically a little bunch of points where each point is a person. And what we're looking for is whether there's overlap between the treatment and control groups. So let's turn to that and talk this through. This, by the way, is from a different example because of security issues with the Danish data, and I couldn't access it myself. Long, complicated story. This is from a different example, but the same point holds. So now let's look at what this figure looks like. The x-axis is the propensity score. This is technically on the Logit scale, which is why it doesn't go from 0 to 1. You can sort of ignore that. Again, each point is a person. So the black dots up top are the treatment units. So those are all the different treatment group members in this example and their propensity scores. You could ignore the sort of vertical spacing. That's done just to allow to see the different points. Below that are the control units or comparison units. And in this case, this was an example of matching as well. And the black diamonds were ones that were picked as a match. And the gray diamonds are those that were not picked as a match. So this is an example that, again, used 1-to-1 matching. And what we see here, for example, is that there is pretty good overlap between the treatment and comparison units. We see across the x-axis, we see reasonable spread in both groups, and sort of we don't have some treated units without any comparison. That's the sort of thing we'd be looking for. This is an example, though, where 1-to-1 matching maybe isn't the best strategy. It looks like we're actually not using a lot of those gray diamonds who actually have propensity scores quite close to the treatment group distribution, those gray diamonds that are sort of in the middle there. But this sort of figure can just help kind of just get a sense for where the data is and how much overlap we do and don't have, and what sorts of methods are going to make sense. So let's now turn back to this idea of covariate balance. Again, the main goal of this approach is to form treatment and comparison groups that look similar on a large set of observed characteristics. And so the key diagnostic that we're going to do is to see whether that happened. I'm going to show you some examples of that. I also just want to highlight that many of the propensity score software packages facilitate this sort of approach. And particularly, there are packages in R that have some really nice features in this regard. Packages called Matchit, Twang, and Cobalt. So you don't have to code all of this yourself. Those packages help you do it. The most common measure of covariate balance is what's called a standardized bias, or sometimes a standardized difference in means. So if any of you come from psychology or education, you might be familiar with the idea of an effect size, which is basically a difference in means divided by a standard deviation. So that's what we show here with this B. So we have the average covariate value in the treatment group minus the average covariate value in the control group for a particular covariate X, and then divided by the standard deviation of that covariate X. And the idea is that you calculate this both before and after your propensity score adjustment. So in our case, before and after we do the matching. The standardization, dividing by that standard deviation, basically just puts all of these onto a common scale, and there's some established standards for how small you want that to be. And we'll come back to that in the next slides. Sometimes people will do things like t-tests, or you might be thinking of your own favorite way of comparing two distributions across two groups. One thing to be a little careful about is that things like t-tests that use a p-value or sort of some formal hypothesis test can be challenging in this context because they kind of conflate balance with sample size and differences in statistical power. And so what's nice about this standardized bias is that it really focuses just on the covariate balance and is not affected by changes in sample size. So let's see what this looks like in our suicide example. This table shows what's called the covariate balance in the unmatched, or sort of the original data, and then in our matched sample. So I will walk us through with just a few of these covariates that are shown here. And you can see, for example, if we look at age 65 plus, we see 2% of the treatment group was over age 65, and almost 9% of the original sort of comparison group. About 8.9% was over age 65 in the full comparison group. And that corresponded to a standardized mean difference, the standardized bias of 0.5, which is quite large. The rule of thumb is that we want that to be less than about 0.1 or 0.2. So this is showing, and as you can see in that SMD column, quite a few of these covariates have substantial differences between the treatment and control groups before we do our propensity score matching. After propensity score matching is what we see in the final two columns, where the treatment group numbers would stay the same because we haven't changed the treatment group at all. The non-PT group, the non-psychosocial therapy group, values look much more similar to the psychosocial therapy group in that first column. So if we look, for example, at our age 65 plus variable, instead of the 9% we saw originally in the comparison group, the subset that we've chosen as matches has an age 65 plus rate of 2.1%, which is very close to the 2%. So again, just to make sure this is clear, the matched non-PT group, these are the 18,000 comparison people that we've selected as matches. So again, we had 6,000 in the therapy group, and then for each of them, we picked 3 comparison subjects. So these matched columns are what are calculated using the 6,000 therapy group members and then their 18,000 matches. And we see in the final column that the standardized mean differences are tiny for all of these, again, as a sign that we have done a good job at making the groups look similar to one another. And I'll particularly just highlight that the 2 bottom rows both have an SMD of 0 because these were the 2 variables that we required an exact match on. So sort of by construction, these match perfectly in our treatment group and our matched comparison group. These sorts of tables can be a little overwhelming though, so let me show you a nice sort of graphical summary that is a common way to present this in a figure form. So this figure is sometimes called a love plot after Thomas Love, who first sort of used this sort of figure. And this basically shows the standardized mean differences before and after the matching. And what's nice about this is it can show it for every covariate. So each row essentially is one of our covariates. The blue circles, the hollow blue circles, are the before matching. So in the original data, the 6,000 treated and 60,000 controls. And we can see that many of those, these are absolute value, many of these standardized mean differences are larger than again, like 0.1 or 10%, which we use as sort of a threshold for covariate balance. So we're sort of worried, and like these blue hollow circles that are to the right in this figure are a sign that there is substantial confounding before we do a propensity score adjustment. The red solid circles are more what we want to see, which is that almost all of them are to the left of that dashed vertical 10% line. Many of them are actually basically right on zero. And so what we're seeing here is that the matching, so the red circles are in the match sample. This is showing that the matching worked in terms of creating these groups that look similar to one another. So again, the blue hollow circles are constructed and calculated using the 6,000 treated and all 60,000 comparison. The red solid circles are calculated using the 6,000 treated and their 18,000 matches. So we can make a figure like this, and they're great to show in papers and things. And this is a nice quick illustration to show that the propensity score method worked. It created well-balanced groups that look similar on this large set of observed characteristics. So then we sort of say, okay, we're good. We think this was successful. Let's now actually estimate the effects that we care about. So what's nice here is that essentially our outcome analysis can proceed essentially treating this data like it came from a randomized trial. So what we do is we take, again, our 6,000 treated subjects and our 18,000 matches. So we can run a regression, regressing outcome on treatment status and covariates. We could do a t-test. We could do a Kaplan-Meier survival curve. Basically, we have our 6,000 and our 18,000, and we analyze them as, two groups, two independent groups. If we did weighting, we would run regressions using the weights, the propensity score weights. If we instead had done subclassification, we would estimate effects within subclasses and then combine. But the main idea, again, is that especially with matching, the analysis you do can be essentially the same analysis that you would have done had you never learned about propensity scores and done any sort of propensity score approach. So just to illustrate what that looks like here, so this is the outcome results for the suicide example. And we see here, again, these are essentially survival analyses using the 6,000 treated subjects and their 18,000 comparison subjects. And we can look at things like repeat attempt after 1, 5, or 10 years, death by suicide, death from any cause. What was gratifying about this study is that it looked like this therapy was actually quite effective at reducing risk for all of these outcomes over even a 10-year time period. So we're not really focusing here on the substantive findings, but just want to illustrate and show you that you can essentially do the standard sorts of analyses that you've learned about in using these matched samples. The Achilles heel here, though, is sort of a potential unobserved confounder. So in order to interpret those effect estimates on the previous slide as causal, we have to believe that there are no unobserved variables related to participation in this program and outcomes, that any difference in outcomes must be due to the treatment and not due to some unobserved thing. We're not going to get into the details here, but I just wanted to highlight that it's possible to do sensitivity analyses that allow you to basically ask how strong such an unobserved confounder would have to be in order to change study conclusions. So just as one example, in this study, we were able to do one of these sensitivity analyses and show that for one of the weaker effects, say repeat self-harm after 20 years, a binary unobserved confounder with about a 50% prevalence would have to have about a twofold association with participation in the program and with the outcome of interest in order to explain the results. So what's nice about this is instead of sort of just vague worries about unobserved confounding and someone who says, oh, I don't trust your results because, I think there's an unobserved confounder, this is basically a way to turn that into a more quantitative statement to then have a conversation about whether such a variable is actually plausible. So I hope that this has helped you see, again, sort of from soup to nuts, from beginning to end, what a propensity score analysis looks like. Again, ranging from the initial steps of defining treatment and control conditions, selecting the covariates to equate the groups on, estimating the propensity scores, using those propensity scores, checking if it worked in terms of creating well-balanced groups, and then finally moving to estimating the effects and then assessing sensitivity to an unobserved confounder. I'm sure you have lots of questions about the details, but again, I hope this at least has given you a sense for these steps and the main ideas of what to do at each of them. Thank you for listening to this session. I hope that you found this workshop helpful for learning about propensity score methods and their application in mental health services research. When applied well and carefully, these methods can help us learn more about what can help improve prevention and treatment strategies related to mental health. To learn more about this topic, you can also take a full-day online course at Johns Hopkins. The link is here. And also, please keep an eye out for additional workshops out of the Johns Hopkins ALACRITY Center on methods topics and other topics. And please also follow us on Twitter. Thank you very much, and I hope that you've enjoyed this session.